One of the prerequisites to really having a strong data science program is having students who can program, having some sort of coding experience, a strong math base, some sort of coding experience, and what we call algorithmic thinking. And that is this idea that every student, no matter what discipline he or she is studying, in the year 2019 needs some foundation into how computers work, some sense about how to program it or what's involved in getting a computer to do something besides what a software package off the shelf can do. And it's in that spirit that we created this faculty learning community out of the Innovation Lab at Spelman, and it brought together a number of different people, including musicians, computer scientists, and from that came this idea of ATAVizM, which combines not only the algorithmic thinking part of it, but it involves data analytics and data visualizations. And that is what we're going to hear today. And that's it, that's my introduction. I'm gonna turn it over to the people who have the expertise in the content matter expert.
Now Jerry will be helping me train faculty from the University of Michigan, Florida State University, Emory, and UGA in the early part of August, as will William Dula. So he's being quite humble about his role. But I'll go ahead and get started on the content, as he was saying. So in music, we talk a lot about Gestalts. Some of you psychologists may know Gestalts. Some other people may know about Gestalts as well. But basically, Gestalt psychology thinks about how we form categories in our mind. You know, cars come in a lot of different shapes and sizes and colors, but we know that's a car, right? So here's a more abstract example of a spatial Gestalt. So it has some sort of handle, some sort of implement. I don't know really what it's called. It's just a made-up object, but you know, we can kind of maybe form a category based on this. Let's see. So here's category A. There's where it's kind of rotated at different distances and perspectives. Here's category B, where the parts are recombined. The handle and the implement are shifted around. Here's C. There's various kind of warpings, I would call them. And then category D, there's various image distortions. How many people think that category A, everything in category A forms a Gestalt, forms a mental category? Okay, one person, great. Two people. What about category B? Okay. Nobody? Great, that's good. C, we still think that's the same thing we saw on the last slide? So can we still recognize the kind of abstract tool, even though it's warped? I would say yes. And I would also say for mental distortion, the one that I would say is no longer Gestalt after these transformations is B, because the individual parts are recombined in a way that it no longer we don't know what the functionality is, but it probably no longer has that functionality. And yeah, so, and you might be reminded of the famous phrase, and it's misquoted, it's actually the sum of the part, or the whole is something else from the sum of its parts. It's often quoted, the whole is greater than the sum of the parts, but it's actually the whole is something else from the sum of its parts. When you combine things in a certain way, it becomes something else from what those individual parts are. So that's very much the idea in music, except for we talk, instead of spatial Gestalts, we talk about temporal Gestalts, okay? Gestalts that happen over time, that are perceived over time. So we have various common equivalence classes. I don't have time to go into those, but most of them stink. Music theory has basically failed. We have all this formal analysis, but we basically failed to figure out Gestalts. You can use very complex similarity relations, but the whole idea of a Gestalt is that it forms some sort of equivalence. So most of our formalisms so far don't really work. So I'll give you an illustration of this. Volume control here. My computer does not have volume control. Okay, so that is the famous theme to Bach's C minor fugue. BWV 847. That probably, Justin knows what I'm talking about. So anyway, so this is a theme, but every time it's repeated, it's changed. So the first interpolation of it is called a tonal answer. So it's modulated to the dominant, and it's also has various little modifications, and it sounds like this. Oh, well, it's not playing. And so those little X's at the top means that although we hear these as Gestalts, pretty much everybody agrees that the subject and answer in a fugue are Gestalt. Our pitch, our transpositional, and our contour equivalence classes that are the common mathematical categories do not work for comparing those two as equivalent. So my solution actually comes from Nigeria, where I did about 2 years of field work, and I'm going for another year in December on my second Fulbright fellowship, and I'm mostly focused on Yoruba and Igbo, which each have about 30 million speakers in southern Nigeria. And so, just to give you a little illustration of how language and music tie in, is the mic still working? Okay. Here's a common hymn that's been was translated during the missionary era to Igbo. One of the things that missionaries really did to evangelize was take European hymns and translate them into the local languages. However, when it's a tonal language, it doesn't work so well. So here's All Hail the Power of Jesus' Name. What they would do is do metric translations. They preserve the number of syllables. So All Hail the Power of Jesus' Name is 8 syllables. Ohakele Ike Jesu is also 8 syllables. However, there's also an added tonal contrast, and you can see the shape of it there. Low, 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 high, 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 low.
Ohakele Ike Jesu.
So if you sing this, and there's the individual disyllable shapes, if you sing this to the common hymn tune, so they would translate it, then they put it back on the same hymn tune, it sounds like this. Oh, well, there's some mismatch there. So instead of getting low high, or it's supposed to be level, the oha is supposed to be level, but instead it rises, and the ek is also supposed to be level, but instead it's ek. You might know this is All Hail the Power of Jesus' Name, but then it's sung in Igbo. So what happens is, instead of all, we get trees, and instead of strength, we get buttocks. So it becomes trees hail the buttocks of Jesus. So here's a little simple recomposition where you get the basic tones, but it's kind of not very musical. So what Nigerians have done is just composed whole new hymn tones, like this one. That are musical and also follow the tones of the language. And here's another funny example. Come to prayer, it's crippled. Okay, so I mean, it's basically every hymn has that. So basically, this idea of how, and you're going to see how how speech can be turned into the talking drum, surrogacy, and into song. In just a minute, we're going to have a demonstration. But this idea of how a contour, a shape, a melodic shape, a pitch shape, can be preserved across all these domains and can be preserved correctly in a hymn is kind of what led me to a novel data science solution to what's been a persistent problem in music theory and even data visualization. So Martin Vattenberg, who's maybe one of the most prominent data visualization experts out there, he heads up Google's Big Picture project along with another fellow, so pretty influential data visualization person. He has a PhD in mathematics, and in 2001, he came up with this visualization approach that could be used for music, could also be used for a lot of other things. And the one example he used is Mary Had a Little Lamb. So here's Mary Had a Little Lamb, Mary Had a Little Lamb. So you can, if you know the tune, you know that comes back. So there's an arc drawn from the opening part, Mary Had a Little Lamb, to later, after little lamb, that part comes back. Mary had a little lamb. So whenever there's a repetition of a pattern, it'll draw an arc in between it, and it's a way to visualize the musical form, which is, and studying musical form is one of the main things we learn in music theory courses, which is 4 semesters in the undergraduate curriculum. So the way he applied this technique, though, didn't work very well. So it works okay for Mary Had a Little Lamb because it's a very simple melody. The melody comes back exactly that, particularly that Mary had a little lamb. But what a composer like Bach does, or what Nigerian musicians often do with the melody, is they vary it. Also jazz musicians. So you can imagine that a composer might not just do Mary had a little lamb, but Mary had a little lamb, or invert it and do these other things, do variations, because music is very much not only repetition, but repetition with variation. So Wattenberg had this great way to visualize music, but because he didn't know much about music, he wasn't able to make it work very well. So the project, he intended to make a web app and all these things, and basically what we're doing now, but he didn't have a way to deal with the data. He just had a way to visualize it. So by using African-centered technology, we've come up with a solution for that. And there's 600 pages you can read about how it works exactly, but we're mostly just going to give a demonstration now. I will show you that this is basically how it works. We use binary comparisons to compare pitch height within a moving window, and by using this method, this is how the computer, that little matrix, that kind of horizontal matrix there, is how the computer sees these themes and makes it possible to see Bach's subject and tonal answer as equivalent. And forming an equivalence class makes the computation much more efficient. And so in a few seconds, the computer can identify all these subject statements. So we're going to listen to this quickly with the visualization, I hope. But the much more interesting, I think, I always use the Bach example because music theorists think it's not relevant to them unless we talk about Bach. But we have a much more interesting example we're going to share with you right now with a performance. So I'd like to welcome Julian Rucker and BC Adeleke. And so every year, the Glee Club offers a commission to sub-Saharan African composers, and this year's winner was Ayo Oluranti. And so this is based, the piece he wrote is based on 7 proverbs. So right now, we're going to show, first of all, we're going to start with the opening proverb, and you can see all the arc connections. So that shows all the places that this proverb appears. So I'm going to read that one. They'll play it and sing it. Then we'll go to the next proverb. And by the end, you'll see the whole musical structure illuminated. So the first proverb means character is religion, meaning religion devoid of good character is worthless. Iwalesin. And so this is illustrates that concept of what I was talking about, that we can speak the tones, we can play them on the drum, we can sing them. Here's the next one. Iwaloba awure. And that one means supplication is important, good character even more. Next, we have character is salient. One's behavior determines one's attitude. Iwalorisha. A man is honorable when his word is his bond. Kawibe, kababe, iyi enionien.
Kawibe, kababe, iyi enionien.
Good conduct is an ornament, meaning it is very valued. The value of a smile is in the whiteness of the teeth. Iwa rereni e sho enion. And the title of the piece means the child begotten by the God of character. Omo lua bi. And I forgot to show it. Whoops. There it is. It's the yellow. And then finally, be certain without doubt. Be uncertain without doubt. Being neither here nor there is undesirable. Oshaka, oshoko, koyeni, raurao.
Oshaka, oshoko, koyeni, rarao.
Thank you very much, BC and Julian. The video, you could just look it up online. It'll be in the AUC repository soon. That's the Glee Club performing. We don't have time to listen to it. So I'm going to hand it over to William Dula to finish out what our next steps are.
All right. Good afternoon, everyone. My name is William Dula. I'm a graduate student in applied mathematics at Clark-Atlanta University. I did my undergraduate work at Morehouse College, and this is where I joined this project. So we mentioned that the focus of this project is to infuse algorithmic thinking and these sorts of data science skills into members of all disciplines throughout the college. And in this particular work, the way we're doing that, the way we're infusing this knowledge, is through allowing students to understand how the software works and organize it in their own way in order to make new discoveries. So I'll describe a bit about how this system works currently. So currently we take symbolic music data, in MIDI or XML, but I think we're just using MIDI for right now. And then it goes through that contour refinement, that binary matrix comparison step, and the user can decide whether they want to just display patterns that they already know exist in the piece, or they can discover patterns. And the discovery can happen a number of different ways, but in general, the user's main input is to decide how long each pattern is. So you can think of that as how exclusive or inclusive they want this search to be. All right. And so once that's done, we just go straight to the plotting, plotting these nice arcs and coloring things according to what pattern they come from, and then resizing them according to how wide or how not wide, how thin the pattern is across time. So for music students, all right, when they're studying form, there are numerous ways in which one could define a pattern, numerous ways in which one could define these sorts of gestalts. And so what we want to do is give them options later on. And particular, we want to give them the option to define patterns by contour, so the sort of vertical relationship between notes, by pitch, by key, so the key center, by rhythm, so more temporal, horizontal representation, or by the chords, so a vertical representation. And we want them to be able to recombine all these different sorts of filters in order to create unique data sets, in order to create unique analyses of these pieces. And perhaps in their own time, they can expand upon these and study these pieces more in depth and come to understand their true structure and the true relationship behind all the ideas that the composer intended. And so that's just one way that we're sort of doing this. So for the project, a sort of update on the project in its whole. So I am in charge of translating this project. There was a version that existed in MATLAB, and we're transitioning that to now Python, more sort of open source way. The MATLAB runtime version is available on the AUC repository, yes?
Yeah,
on GitHub. And so users can read this code and they can implement it themselves, and if they download the runtime, they can run it themselves. But we want something that's a bit more modifiable, a bit more in line with these sort of open source philosophies that are rising up today. And so that is my job right now, translating this into Python. And the current goal is to have a downloadable version ready by August, when we will be training faculty on how to use it and implement it in their curriculum. Next steps will then be to deploy the app onto the web, so that it won't just be the faculty that come to our workshop, but so that educators around the world and around the country can use this. I believe there's about 300,000 music students in the US currently, and we want them all to be able to use this in their education. And then in the future, what we want to do is set up some sort of database, some sort of data collection system, so that when users, this is essentially annotating the data, annotating these pieces. And so we want to collect those annotations, collect these analyses, and then use them for further works, further research. And so perhaps some learning can be done on various patterns that are found for a particular composer, or students could use this to see, well, what sort of dominant patterns did a composer use during this period? What sort of things are prevalent in these regions? All these sorts of things. And so we want to create a larger repository of information for these pieces later on down the road. And that is, in a very short time span, everything that is happening with this project, this wonderful, wonderful project. And I feel very privileged to be working on it. So I just want to thank you all for listening to us talk about our work.
Thank you.
Really a phenomenal opportunity. We started out by saying our faculty is already working on data science, but I think this is a really important kind of observation here, in the sense that our students are learning music differently than what I probably learned it in terms of music theory way back in the Stone Ages. But that's really phenomenal about how we're taking a traditional idea around music theory and then thinking about it in a algorithmic format, and how that is being composed. So thank you so much. Once again, a big hand for all of you in our performance as well.